Hello, hello. Can you hear me? Can you hear me? Hello. Okay. So today we'll be presenting on Wasserstein Coreset. I'm Harshit, he is Shasmith and Saketh. So Coreset is a small representative of a large data set. Without losing much information, uh, it can be helpful in reducing training time. So the main goal of it is there's no there's so the main goal is to make sure that the posterior of the core set is similar to the posterior of the large data set. Here as you can see, pi naught of theta is prior, and fn of theta is the log likelihood of data set, and to the right is the same equation, but weights are associated with each log likelihood, such that the weight vector has the zero norm of the weight vector is much less than the total data set size. So the paper will be presenting is Bayesian core set construction via greedy iterative geodesic ascent. So the current limitations of existing core set constructions is that they underestimate the posterior uncertainty. So various methods this is explained in later slide. So the Bayesian core set problem here we have. So initially Bayesian posterior equation is given where ln is the log likelihood of a data set and L theta is the summation of the log likelihoods, and next we associate weights with each log likelihood. The same way, the optimization problem here is we try to reduce the 2D norm of the original log likelihood sum minus the weighted log likelihood sum, such that the each weight associated is positive and the zero norm is much smaller to the original data set size.
So from here on, I will start. So in this paper, they will first show the problem with this optimization problem. This optimization problem were used in different before papers, which are weight and Coreset problems, in which they use the constant. They use a simplex constant, that is, they use the weighted, like the sigma and w. They use the constant, the norm of total L vector. So not sorry, the norm induced by the weighted Coreset problem is equal to the sum of norms of all the log likelihood, and they will ensure that the weights are zero norm of weights are less than m. This is a simplex constant, that is like it's a linear combination of constraint, and the paper proposes that if we use this constraint, then uh, then there will be overestimation of points and we would be adding too much additional data into the weighted core set. Uh, so this is because the while solving this optimization problem, instead of scaling the selection with the norm of likelihood, these will be scaled in terms of norm of sigma. Here sigma is summation of all norms, right? but uh, what we actually want is to scale it with norm of sum of all the likelihoods. So this paper proposes that this simplex constraint problem would give a overweighted one, and hence we will introduce a new radial optimization problem in which we get a constraint of instead of okay, so I will now tell what the radial optimization problem will come. So first, this we will show that by scaling alpha with the weight vector, we will not change the zero norm. That is, the norm of alpha w, the zero norm of alpha w will always be less than or equal to zero norm of w, because when alpha is greater than or equal to 0. So, and hence we will scale all the w vector with alpha, and hence we will propose a new optimization problem in which we will minimize alpha lw minus l log l whole norm with respect to alpha and w. And now, to minimize this problem, we will find the optimal alpha, so that this norm problem we simplified it to a much simpler problem. So the optimal alpha found out to will be uh, is here in alpha star, which is it is kind of a relative norm between the L, W and L. Okay. So now if we substitute this alpha star into the main optimization problem, we will arrive at optimizing uh, we will arrive at finding the maximum of uh, LW and L. LW is a unit vector of uh, like that is capital LW. Here capital LW is the log likelihood vector of uh, log likelihood vector of L. So I forgot to mention one thing. Here we find L using Monte Carlo sampling. So we will be this LW vector will consist of S vector, S dimension. So where S is the Monte Carlo sampling size. So now we will try to minimize. We will try to maximize L, the LW in a product closeness between LW and L, which is similar to, we can think this problem as similar to aligning the LW vector with L. So this is what they state, and we are also adding additional constraint known as no norm of LW equals to 1, and this is the constraint which will add the radial optimization problem instead of simplex constraint given in the before slides. So uh, now our main problem will be to align LW and L. So we will now uh, first find DT and DTN, where these DT and DTN are geodesics. Geodesics is nothing but it's a fastest part between 2 points in a space in constant time. So it's, for example, it's a straight line in our Euclidean space. So now, huh? No, this is for a general manifold. So we are trying to go into a general manifold from straight line. So dt will be the geodesic from L to LWT, where LWT is, now we are introducing the algorithm. So LWT is the iteration. Okay. So, and DTN is nothing but aligning with LN with LWT. LN is nothing but the point, likelihood point at that point. So now, to find the solution to this optimization problem, we use line search method. So uh, we will first find the combination of LWT plus a convex combination of LWT and LNT LW2 and LNT, and we will try to align it with L is the normal vector. Okay, and solving this gamma, we will get the following optimal gamma, which is uh, C, which is given below. So it is basically like a problem between it's a function of three inner products which are there here, like LLNT, LLWT, and LNT, LWT. And now we come to the algorithm, main algorithm part, which is greedy iterative of the geodesic ascent, in which first we normalize the likelihood vectors and initialize the weights to 0, and we first compute the geodesic direction for each data points, and then we choose the best point in which this geodesic aligns with the original. We choose the point in which ln is aligning to L, and we then uh, perform the line search method, and finally update the weights of this core set, uh, and we update the core set to iteratively find the uh, other points in this core set. So, and finally, as we
So, one question. So, all this way is being done at the instance level, is it? Not at mini batch.
unknowns, like I didn't get your question.
This for each data point, it's like each data point, which is very impractical. Compute the geodesic distance for each data point.
Yeah, so it
Many of these
will,
approaches they create their own mini batches, and then at the mini batch level, you may compute this
but
direction.
we have to find the data point which is maximally related. Like we are finding the core set, right, sir? So we
I
have
understand
to.
core sets are often done. I'm saying at the level of mini
Okay.
batches, and not the level of data points will be too much. I deal with at such a large scale.
Yes, sir. Like yeah. So here we are scaling it with O of n. Um, like we can like do it for each subset points and maybe decrease the complexity of this.
The
Uh,
other question I have on the slide is, um, I mean, what is the convergence criteria? This is for t equals 0 to n minus 1. What is that?
sir, they have like let me they have shown like what uh, sorry sir, like they have given the convergence criteria. I think we didn't present it, I think. So basically uh, like uh, this is seen in perspective of geometrical sense. So like in each step we will be uh, more aligning to the core set, right? Like we are trying to choose the maximum data point uh, which aligns with this. We are trying to choose the maximum data point which has maximum alignment with the original likelihood. So this first we are starting with zeros, right? So in the first step we will be uh, in the first t equals to 1 step we will be getting the maximum point, maximum the first data set point, and in the paper they will prove that this error will decrease like as we are removing the first data set point, then the uh, error between the posterior things will be always decreasing. So like it's like as we are removing the most aligned point from the first state, the error between the core set point and the full data set likelihood will always be decreasing. So I forgot to add this point. So yeah.
They have some theoretical results just
Yeah,
showing the decrease, but
yeah,
not the rate, nothing, right?
yes. So mm, next we come to another algorithm
How
which
many papers you have? This is the
we
second
have.
one.
Yeah, this is the we have three papers. So this is the second paper. Yeah,
You can run through this very quickly.
yeah.
This
So
is the present, but don't spend too much time. Yeah, this looks really old.
yeah, it's okay. So this is another paper in which we will be um, presenting sparse variational inference. Most of the core set problems and the optimization problem will be borrowed from the before paper, except that now instead of minimizing the
You should spend a little time preparing your slides nicely. The seminar carries some weightage.
uh,
Why such patchwork, right? Copy paste or something. I mean,
sir, like
prepare it for later.
we thought our presentation is late, so we were planning to do the
Late
need
means when.
around 6. So with
Come on, I mean, it's in the beginning of semester, right? This is not late, is it? Really?
so we were trying to format it with nice and so
Go ahead.
okay. So now instead of minimizing the uh, likelihoods between L and log likelihoods, now we will try to mini, mi, go to the original problem, that is the weighted probability distribution. Pi w is weighted Coreset probability distribution, and we are minimizing the KL divergence distance with the original distribution of the data set. So now expanding this and going to some steps of equation, we find that uh, this problem reduces to problem of maximizing covariance between F and F transpose. In this paper, F is the potential instead of L. So F this is nothing but uh, we are choosing the maximum correlation point, which has uh, we are choosing the point which has maximum correlation with the residual error uh, of the distance between data points. And uh, now I'll maybe directly present the algorithm, since we are so in this algorithm we will first do the Monte Carlo estimation of this uh, posterior, and then we will estimate the correlation using this Monte Carlo sampling. And here GS is nothing but uh, F minus expectation of F. So that too we are also, and that is also we are approximating it with the Monte Carlo estimation. After finding the correlation, uh, we will choose the best correlation between in this uh, best correlation in this point, and then we will add it into our core set, and then we will do the reweighting for the posterior, uh, which is shown here. That is, we use gradient step for uh, uh, decreasing this gradient. Okay, so now I
The main everything seems to be run of the mill except for step 7, right?
steps.
Correlation between potentials and residential error, and then 8, which is add the best X potential to the core set.
Yes.
So 7 and 8 is the main difference.
Yeah,
Right?
7 and 10 may difference between.
There's kind of
Yeah.
renormalizing based on
Uh, so now we go to the pairwise.
Hello. Yeah, so the motive of this fairness in the motive of this paper is to target the fairness in Coreset problem. So in cases where the use case is related to social um, social nature, we want it to be unbiased in terms of the data, the representations of different geographic uh, divisions. So sorry, demographic divisions. So um, the we want all the subgroups to be represented equally. So this might be a problem during construction of Coreset. So yeah, so this is the motivation of the paper, and one of the existing methods ensuring fairness basically cluster the data set into groups based on the demographic divisions and make sure that each all the subgroups are represented. And the problem with all of these existing work is that although they might guarantee that all the subgroups are represented, their performance across the downstream task is under doubt because the uh, the proportion of different subgroups in the new corset is different from that the, uh, in the original data set. That so sorry, the class um, the class balance is disturbed. So this paper introduces fair Wasserstein corsets where they generate synthetic representative samples, but also assign sample level weights. And yes. So just a notation. So here pz of theta is that of the corset, and this is basically weighted average of the direct delta functions, and similarly a similar representation of the original data set, and the sample is represented as z, which is basically the d, which is the demographic classes, and x, which is the input, and y is the output. And we are considering it for classification type of tasks, so y and d are both discrete. And this is basically the Wasserstein distance. Do you want me to skip this? Yes. Okay. Yeah. Yes. So the constraint that they add for ensuring fairness is basically the j that's here. So the j is calculated between the conditional distribution of y given d and y, and the j is large when there's for different divisions. The p uh, yeah, see p diverges extremely for different divisions. So by adding this term as constraint less than or equal to epsilon, so epsilon is the parameter that determines the maximum fairness. So they the final optimization problem can be formulated as given below. So we minimize the Wasserstein distance, which ensures quality of corsets, and the constraints ensure the fairness of the corsets. And this is further reduced using 4 steps. So firstly, yeah, so they say that in using this lemma, um, any pair of m data points z, the best Wasserstein corset using this is less than the best pair Wasserstein considering all possible data points, which is all possible values for d and y variables. So they want to reduce the size of the feasible set of the optimization problem. So they first fix the d's and y's and subsample the um, feasible set from the set from the original data set. So
So
this
I don't understand this. I mean, the whole idea was that, I mean, when you pointed out the issues with most of the core sets approach, they do clustering and they may not represent all the distribution, the classes fairly. But here you set the proportions in the core sets to be similar to the respective proportions of original data set. Are we not facing the same problem? I mean, wouldn't you rather do it on some validation set than the original data set? Or, like what Pratik, you have already in doing, you can consider privileged and non-privileged. Then ideally you're clearly calling out, these are the privileged in the sense these maybe get potentially ignored, so I'm going to boost them, bump them up. But this, I'm lost. I mean, after all of this, you're kind of again making proportions similar to respective proportions of original data.
Yes, sir. So this,
Isn't that creative? Or if you have a counter, you can counter.
yes, sir.
So for me, this is like an anticlimax.
Yes, yes. Um,
No,
y-
I mean, disagree with me, agree with me.
uh, yes, sir. So initially, the problem of this demographic disparity is thought to arise from the Coreset calculation method. So I don't think they assume that they propagate from the original dataset distribution. So I think,
But then how is it fair? Sorry, I didn't get your point.
I
I
mean,
couldn't hear you properly.
yeah.
How
So
is it fair?
they assume that the original dataset is fair, and by adding this additional constraint, what the unfairness that may arise in the Coreset calculation method algorithm is eliminated. I think that's the unfairness they want
Okay.
to target. Yes. So and then they refer to a paper saying that this constraint can be reduced to a linear is equivalent to a linear constraints on theta. And similarly, they said that the Wasserstein distance can also be equivalently written as this inner product of the cost that is involved in the Wasserstein and the probability measure, and the additional constraints. So that they again refer to another paper and said that which constraints. So it yes, yes. So that's the reformulation of the first three constraints come from the reformulation of the Wasserstein minimization objective. The fourth a theta greater than zero. That's our additional constraint that we're adding constraints. These constraints. So so this minimizing of WC. This the
I think that is just preserving marginals, right?
okay,
So do you understand what? Oh, sorry, you asked. So you
okay.
know what this constraint P one m equals one upon
So
n.
they didn't really build on this. They
But
just
isn't that
referred
just
to a
preserving marginals? So did you spend some time? See, one is slides you were making at the last minute, but did you spend time reading, understanding?
like this paper. There was actually a problem. The original paper that we got that was submitted to TMLR conference, and it was necessitated that we only present from NeurIPS, ICML, and
No,
ICLR.
no, DMLR is okay. I mean, DMLR is rated A star. No?
I mean, this was so we had to read the paper in the last minute. The paper I was able to read, but I wasn't able to look through the papers cited from the paper and the results
You
as
can
well.
always check. Na? So DMLR is fine. So what was that paper on?
The paper on using Sinkhorn loss. Yes, yes. Uh, I don't think I don't think they reformulated in this way as in our product. Okay. Okay. Okay.
Yeah, anyways, I mean, if it was an original paper suggested, you could have at least checked if you're DA, right? You have suggested a DMLR paper and is it an A, right? So you could have checked with him. Instead of just
Yes.
Fine.
Yeah. So yes, yes. And this is the algorithm by where they minimize convex surrogate for the objective. The experiments, so they compare with just the clustering based methods, existing clustering based methods. So there is a trade off between the demographic disparity and the AUC metric. So and so we see that uniform random sampling gives a good AUC, but it has a problem of demographic disparity, and the clustering methods which are designed to ensure having no disparity, they have less AUC. So this they consider as a sweet spot amongst all the methods. Uh, that's it. That's it. Yeah. Yeah. So for projects, we are working on the original paper that was shared. So in their paper, they just didn't have any baselines. Wait,
But just comparing,
You
uh,
just want to compare the Wasserstein with the
that is certainly baseline. I mean, I don't know whether you should compare all of them. Translation is really good. I will not spend time on that, right? Consistent courses makes sense. Certainly, I mean, this is consistent courses are the most useful, right?
yeah.
Again,
That
that's
was
what we representative was.
fair Wasserstein.
favor.
Sorry? Fair, huh? Okay, okay. So that we have not implemented.
Yes, yes.
That where was that published?
It was new rips.
20? 24, that's right. Um,
So we were trying to
that's great to have comparison, but fast variation you could drop from here.
Okay, sir.
Instead, you could use pair.
Yes, sir. Uh, and is there is can you suggest any um
Sorry?
can you suggest any areas that you can work on from the papers that we presented?
Can they actually do it on our data sets instead of just doing it on MNIST synthetic version which have no semblance to what we possibly will need. Right?
Okay.
We do it on text data sets. If we can connect it to Piyush, Piyush should be directed. Courses for we direct them to Piyush. We can put a message on the group. Piyush will be happy to.
Yes, sir.
His team, maybe someone from his team. Okay, but I think they could work on this. All the courses people do curriculum because some of the things become independent of the LLM training also, right? Yeah. Let's do some more meaningful work.
Yes, sir.
Yeah, you can always measure all of this.
Yes,
I
sir.
think it's good. Yeah, you can do that. You can.
Yeah.
Okay. Clear, right? I think we connect you. But on the theory part, you could still be. All these courses, I don't think Piyush will be. Like you get